going to talk about, as the title suggests, dream materials. There was something in the title about fictional compounds that I will explain a bit later. But the first thing that I would like you to take away is that whenever we have any new technology, it comes with almost like a wish list of new materials that need to go with it. So for example, if you want to make something like a foldable smartphone or something that you can roll, you need a material that's flexible, transparent, solid, electrically conducting, and can emit light, so it can act as a display. And if you want it to be a touch screen, you also need it to be capacitive or something like that, so that it can detect your touch input. So that's a fairly long list of properties that you need a single material to satisfy. Similarly, if you're making aircraft wings or body of a spacecraft, you need something that's lightweight, you need something that's strong, durable, does not crack easily, things like that. So any technology will come with a wish list. So for those of you that are regulars here, 3 years ago in the same place, I gave a talk on time machines. And sorry to report that we have not made any progress on that front. But whenever we do, I'm sure it will come with a list of materials that we need to build one. And we don't know what that list is at the moment. So now that I've convinced you that everything comes with a wish list, let's go on to the more important question, which is how do we find materials that satisfy these properties? So there's an infinite number of materials that you can have. Here's a periodic table, and it has lots of elements. And these elements can bound together to form compounds. And you can also have mixtures of these compounds in different proportions. So for example, water is a compound made of hydrogen and oxygen. Salt is a compound made of sodium and chlorine. And you can mix them together to get salty water, which is a mixture. And so by combining these elements in different proportions to make compounds, and by mixing elements and compounds, you can get all sorts of different materials. It's infinite. And I also said crystal structures because it's not just what is the composition of the material, it's how the atoms that make up the material arrange themselves that can also change its properties. For example, graphite and diamond, they're both just carbon, but the carbon atoms are arranged differently, which gives them very different properties. And so you have lots of parameters to play with. And if you were to go brute force, like let's try every possible combination, it would take billions and billions of lifetimes to search for the one material that you need that satisfies, the wish list that you have. So clearly we need something smarter. We cannot just brute force our way through elements and compounds, and not just billions of years, but probably billions of dollars as well. So how do we go about doing it? Well, one of the most obvious ways is to just look for materials that exist in nature. So wood exists in nature and people use it to build stuff. All sorts of materials exist in nature that you don't have to discover. They're just lying around in front of you. The second strategy is to mix things that are available in nature. And this was done before we had anything that resembled material science. So for example, thousands of years ago, people decided to mix copper and tin, and they get bronze. So you don't just mix them, you have to melt them together and form an alloy. And it was done thousands of years ago. And it was done probably by someone whose thing was to just melt materials and mix them together and see what happens. There was no reason why mixing these two things would give you something that's stronger and better than the things that make it. So it was basically discovered by accident or trial and error. And even though there was no material science, we did know some things. For example, people discovered that mixing copper and tin in a ratio of 85 to 15 gives you the best kind of bronze that they needed for then. And this discovery was so important in the development of mankind that historians have named a whole age over it, the Bronze Age. Right? They could make tools with it that worked. And so that's how we did things thousands of years ago. Now fast forward 5,000 years, and you might be familiar with Thomas Edison. And his story is almost almost an inspirational story that we tell kids about the rewards of perseverance. When he was trying to find a material that worked inside his light bulb, he just brute force decided to try thousands and thousands of materials and find one that worked. And eventually it was carbonized bamboo wood that happened to give him what he wanted. But that's brute force, or trial and error, as we professionals like to call it. Throw a bunch of stuff at the wall and see what sticks. And so that's how we did things for 5,000 years. And but I hope you appreciate that we do need something better, even though this is the way we've been doing things. So I want you to quickly now put on your thinking caps and try to think of a material that is solid, transparent, and electrically conducting. Okay. So you don't have to come up with a new material. Just think about all the materials that you know of, that you might have seen in day-to-day life. Can you think of a material that has all these properties? And for those of you that are actual physicists, yes. Yeah, ice. So ice is not actually conducting, but yes, sea ice, if it has salt dissolved in it and it sort of starts to melt, if it has salt embedded in it, it might be conducting. So yes, that's close, but pure ice, no. And yeah, good guess. But one of the reasons why it won't work is because if you actually put it in a room, it'll melt. But yes, it will indeed conduct. Can any of you think of anything else? Yes. Sorry? Aha, so that's a material scientist. Thank you. Yes. But before I tell you what the material is, which someone already said, let's think about why you would need something like this. So first picture actually shows an airplane window. Have any of you seen an airplane window and wondered, why is it always so oily? Like, it has all these colors, it looks like there's oil stuck on it. It's actually not oil. It's actually a heating element. So you want something that can carry current so that if the window gets frosted, if there's ice collecting on the window, you can just pass current through it and just melt the ice electrically. Touch screens of LED smartphones with LED displays have this material. Some time ago, some companies decided to come up with smart TVs. No wonder that idea didn't take off, but that's something you can do with this. And you can also make solar panels, the surface of a solar panel. And yes, that is indium tin oxide, as you correctly said. And this was also discovered, by the way, by trial and error. So all the way until the 90s, trial and error was the only way to find new materials. And I want to say at this point that this is a bit different from chemistry. So when we talk about material science, it overlaps with chemistry, but it's not chemistry in the sense that chemistry is concerned with finding out how to make a material, how to synthesize a material, for example. Whereas when Edison was looking for something to put in his light bulb, he was looking for a material. He didn't know what to use. And so it's a slightly different problem, even though there's overlap between these two. And so in a way, material science was effectively chemistry up until some time ago. And physicists came into the picture and they started contributing. And I'm a physicist, so I'll tell you about how we did it. But let me first give you a picture of what material science looked like. So, well, this is sort of what it looks like. So we know some properties of some materials. We know, for example, mixing metals gives you alloys which have certain properties, like they melt more easily, or we know, we have the periodic table, so we know that things in one row of the periodic table will sort of have similar properties. So it's not like we're completely in the dark, but we only have a very incomplete picture. It's like a map that's not been fully explored. So for example, you know that Chicago is next to water, you know that Gary is next to water. Is it the same water? No one knows. Or let's say someone in you haven't even discovered South Bend yet, so you don't even know it exists. But let's say someone is in Elkhart and they're looking for water, you don't know what to tell them. Where should you go to find water? So what we effectively need is a map of material science. almost like a satellite image, where we know every single material that exists without actually making it. We can just have a picture of what it will be like if you do this. And so if someone in South Bend needs water, you can just say, oh, walk 50 miles to the west and you will reach a water body. Or if you're looking for a mountain or skiing, just go off this map. There aren't any here, right? So you need maps like these for material science, and we don't have that now, but this is what we would like to have. And this is where I come to fictional materials. So I thought that there would be a substantial overlap between people who attend lectures like these and people who are science fiction enthusiasts. So there was a Star Trek reference, and that is transparent aluminum for those of you that have seen this film. So some people, they need transparent aluminum to hold a lot of water because they're taking whales back into the past on a spaceship. And so they just go and they punch in something on a computer and out pops the formula for transparent aluminum. And this is the dream of material science, computational material science. No, not the transparent aluminum, but the ability to just use a computer to come up with a material that has the properties that you desire. And this is where physicists come in. And physicists have a slightly different approach towards material science than whatever I've talked about so far. So think about the key discoveries in physics, or the great moments in physics in the last decade. We discovered a black hole. We took a picture of a black hole for the very first time a couple of years ago. These were predicted in 1916, and they were a prediction of Einstein's theory of relativity. And we were only able to take a picture of one in 2019. So it took us 103 years to find one. Well, we had indirect signatures of some before that, but this is the first direct observation of one. Same goes with gravitational waves. Okay? These were first discovered in 2016, again, led to another Nobel Prize in physics. And again, the theory, they were a prediction of Einstein's theory of relativity. And it took us exactly 100 years to find them, to actually observe them. Same goes for physics at the tiniest scale. So physicists, they don't just talk about stars. Astrophysics is just one part of physics. There's also high energy physics, particle physics, where you ask, what is a material made of? And you say, okay, it's made out of atoms. What is an atom made out of? And you say, okay, it's made out of subatomic particles, electrons, protons. And you keep asking that. You say, okay, you keep asking these two questions. What is it made of? And what holds those things together? So in case of an atom, you say, okay, it's positive and negative charged particles, positives and negatives attract, and that's what's holding an atom together. And then you ask, okay, what's holding the positive thing together? And you get nuclear forces. And so physicists have done that for a while and asked, what is it made of and what holds it together? And we had some discoveries there. We discovered the so-called God particle, Higgs boson, in 2012. And its theory was developed in 1963. So it took us about 50 years to find it. Similarly, pentaquarks are another discovery of particle physics. So they're, again, a collection of subatomic particles. And it took us about 51 years to find them. And so physics has always been, theoretical physics has always been ahead of experiments, at least in some areas of physics, the tiniest scales and the largest scales. And this led to some arrogant physicists claiming that physics explains everything, from subatomic particles to galaxies and black holes. And they just ignored everything in between, where frankly, it's embarrassing. So some of you might have seen this demo of superconductors. Right? Superconductivity was first discovered in 1911. And some people explained it in 1957, 40 years after it came, but only for some materials. We still don't know how many other superconductors work, especially the one in this demo. We still don't know at a microscopic level what makes it work. How does it act like a superconductor? Same goes with magnetism. It was discovered by ancient Greeks. And again, we have some models for magnetism, but even today, we don't have a full picture of what makes a magnet work. So we have explained everything at the tiniest scales, and we have explained everything at the largest scales, and there's a lot in between that we haven't explained. Do you have a question? So this superconductor is called YbCO, yttrium barium copper oxide. It's a complicated material, but the reason we use it is because you have these tanks of liquid nitrogen, and this superconductor cools down. Sorry, this material becomes a superconductor at liquid nitrogen temperatures. Now, many other materials can be superconductors, like aluminum or mercury, but it's really, you have to cool them down a lot more in order to make them superconducting. So when we give demos here in this room, for example, we only use high temperature superconductors. Thank you. So yeah, so these are some things that we still don't know. But we have some ways to figure it out. So if we know how atoms work, and we know that everything is made out of atoms. Okay, so for example, that's salt over there. If you zoom in and you zoom in a lot, you will see that eventually it's made out of atoms. And we know how atoms work, and we know how atoms collide with each other, how atoms attract each other, and so on. We should be able to figure out how any material works just from the fact that we know how atoms work. That's the dream, right? And there was this quote that even we are made out of atoms, and we know how atoms work. And so it's a philosophical quote that says, a physicist is an atom's way of thinking about itself. But it is true. So what can we do about that? So the first thing you need to realize is that atoms are different from regular stuff. Okay, so atoms and subatomic particles behave fairly differently from regular stuff. So for those of you that come to these talks, you might have heard a couple on quantum mechanics or particle physics, and you might know some of this. But just to give you a 2-minute summary of exactly how they're different, the first way in which they're different is superposition. Superposition just means that everything is not necessarily in one place at one time. Some things can be in more than one place at the same time. So this is a nice cartoon of a skier, and you can see his tracks. You can never see what happened to the skier as he was passing that tree. You can only see that there was a moment when he was behind the tree, and now he's in front of the tree, and you can see his tracks. But you can never see how he managed to do what he did. So this is one fundamental way in which atoms behave differently from stuff that we're used to seeing in real life. The other cartoon is a Schrodinger's cat. If it means anything to you, if not, ignore it. And the other fundamental way in which atoms differ from regular stuff is entanglement, which means that two things that are distant from each other can affect each other instantaneously somehow. And that also plays a role in some properties of some materials. But these are the only two ways. There's nothing weird about atoms that's weird in a way that is different from these two things. So everything that's weird about the atomic world is a combination of these two things. There are no more ways in which it's weird. And so if you know this, you've learned all there is to know about quantum mechanics, except for all the math. So, so now let's go on to our goal, figuring out how materials work from how atoms work. And that presents some challenge. So for example, a teaspoon of stuff, like any stuff, like water, salt, sugar, has about 10 to the 22 atoms. That's billions and billions and billions of atoms. And we need to work out how the collection of such an enormous number of atoms will behave based on what we know about how single atoms behave. And we hypothesize, and so far we have seen that this is true, that all the properties of materials just arise from the motion of atoms and subatomic particles. But again, they're not regular motions. They're those weird kind of motions that I showed you on the last slide. But every property of every material can be explained just by the motions of these atoms and electrons and subatomic particles. Okay. And there is a way to do such calculations, not by hand, but with a computer. It's called density functional theory. It's one of the ways in which we deal with this complexity. And we're able to understand and predict many properties, or most properties of materials with this. And I'll tell you how this works in a moment. But there are some that we still don't understand, like I showed you a couple of slides ago. We still don't understand superconductivity and magnetism, but we do understand most properties. And needless to say, we need some really powerful computers to accomplish this. I have a quick trivia question. What is the fastest supercomputer in the US mostly used for? So it's an IBM computer called Summit at Oak Ridge National Lab. Any guesses? The name of this talk is a pretty big hint, which almost led me to not including this question, but it's actually materials research. So we need some really powerful computers to do this. And we'll come back full circle at the end of this talk, but that is one way. And more companies are now starting to do this. So in particular, I know these three companies employ techniques from computational materials physics to develop their products. And I know because I'm looking for a job there. So I know that these do, and there are many more. Okay. And even though we don't understand superconductivity, magnetism, and a few other things, there are so many things that we do understand from physical theory, such as hardness, strength, flexibility, elasticity, electrical properties like conduction, optical properties like what color a material will be, how much light will it absorb, will it be transparent, what is the transfer, how much can you pull it before it breaks, and so on. So there's a whole bunch of properties that you can find using basic physics. And so let me give you an example of one material that we discovered using these techniques. And this is a material that I actually work on. So it's a phenomenon called superfluorescence. So I'm assuming that many of you are familiar with regular fluorescence. It's these glow-in-the-dark stars that some children put on their ceiling, or you might have toys that glow in the dark. So in the day, you almost let them charge, right? You put them in sunlight or you put them in regular light, and somehow they get charged up. And then at night they glow. And by the time it's late into the night or early morning, you'll see that they've stopped glowing. And then the next day they recharge again and they glow all night. So that's what fluorescence is. You shine light on something, somehow it gets charged, and then you turn off the light and it glows. Okay. So zinc sulfide is one such material that glows. And it exists in nature in some ways, and that's how we found it. But there are these materials, cesium lead halides, or cesium lead chlorides, bromides, and so on. These materials don't exist in nature. Nothing even close to such materials exists in nature. They're completely man-made, and they were first discovered sort of accidentally, but we didn't know that they were superfluorescent until we used our computational techniques that I referred to before. What you're seeing in this picture, though, is just regular fluorescence. What's superfluorescence? It's the same difference between a regular lamp and a laser light. So I have a laser pointer, okay? And you can see that the laser light, I won't point it at your eyes, but you can see that the laser light is different from the light emitted by regular lamps. And this sort of cartoon shows exactly how laser light is different from regular light. So the light from lamps is fairly disordered. So you might have learned that light is a wave. It's an electromagnetic wave. So it's just like a radio wave or your TV waves and so on, except that your eye is the antenna for light. And so it's a wave. And the waves that are emitted by all these lamps in this room or candles or any other light source that you might have, the waves, their crests and troughs, they don't overlap. They're all over the place. But the laser, they all exactly overlap. The highs and the lows exactly overlap with each other. And that's what makes lasers special. Now, these materials, when they glow, they emit laser light. So they get charged up, and then when they glow, they emit laser light. Now, these materials, they're useful for various applications, one of which is quantum computing. So for those of you that know about quantum computing, we need something that behaves like this, something whose waves are all aligned with each other. And a quick burst of lots of light waves that are all in the same phase as when the highs and lows align, can be used for many technologies, including quantum computing or quantum measurements and so on. And this is a cartoon that someone made, a manga artist going by the name of Hayano, and a Japanese manga artist made this cartoon. So it's like fireflies. So a firefly is like a single fluorescent thing. And these materials that are super fluorescent, think of them as a bunch of fireflies that have come together. And it's different from all the fireflies, blinking in unison. It's that somehow all these fireflies have come together to make a giant super firefly. And when it emits light, it's so perfect that all the light waves are aligned with each other. So it's different from having 5 lamps. It's having 5 lamps that have somehow come together to emit super light. Okay. So this is just one example of a material, and I came up with this example because I work on it myself. This is my thesis project. But there are many other materials now that are being discovered through theoretical physics, through computational material science. So some of you might have seen commercials of the new folding smartphones that Samsung has come out with. And glass or anything, any sort of display, it's not supposed to be bendable, right? So this goes back to the example that I was giving you before, where I asked you to think about a transparent conducting material. It's so hard to find because most of the materials that are transparent just happen to be insulators like glass or plastic or ice. And then most things that are good conductors like metals and so on just happen to not carry electricity. And theoretical from physics, you can get some reasoning behind it as to why this is the case. But now that we have these computational techniques, we can find materials that satisfy our properties. And so these folding smartphones and transparent TVs and so on, well, they're the result of computational material science. The last thing, this is the last topic that I want to talk about, and that is computer chips. So computer chips are made mostly out of silicon, which is just sand, basically. Sand is silicon dioxide, so you can get it from sand. It's really cheap. And silicon, each silicon atom has 14 electrons. You might think, well, 14, that's not too many. Unfortunately, it's 13 more than what we know how to work with. Okay. We only know what to do when you have 1 electron. Even if you have 2 electrons, you cannot do anything with pen and paper. You have to use a computer. And so silicon with 14 electrons is already a very difficult material to predict its properties, at least by hand. So how do we understand how silicon works? We use computers. Okay. So when the first computers were being made, we had almost by trial and error discovered some properties of silicon. So for example, we knew that if you add some boron or some phosphorus to silicon, it becomes a better conductor. So silicon is a semiconductor. So we had discovered some of these things, and we had discovered some properties that allowed us to make a computer, roughly. But it's not enough to have a rough computer. You want a reliable computer, you want a fast computer. So it's not enough to have an estimate of, oh yeah, let's mix some boron and see what happens. You need to know exactly what properties it will have. And again, brute force is time consuming. So people turned to simulations, and they ran the simulations on computers. So in a way, computers allowed us to make faster computers. So in a very practical sense, we used slow computers to figure out the properties of silicon that allowed us to make faster computers. But it's more than that. It's that we wouldn't know the properties of silicon atoms if we didn't have computers. Okay. So in a way, computers have helped us understand why computers work. So it's like the physicist is an atom thinking about itself, but instead of it's happened at a very practical scale. And I want to close by saying that if these methods are so great and they work so well to find materials that we need, why haven't we solved all the world's problems? Right? We have energy crises. So why haven't we found materials that solve the world's energy needs, that allow us to capture sunlight or other forms of energy efficiently? Or why haven't we satisfied every need that we have? The reason is that, like everything else, this has its own limitations. So it's a work in progress. As I said before, there are still many properties of materials that we haven't understood, and there are many things that we don't even know that we don't know. And another issue is that in all these cartoons that I showed you before, our materials are just so perfect. But in real life, materials are not perfect. They have all kinds of defects and all kinds of imperfections. So if you have silicon, it's not 100% pure silicon. It has some other atoms sitting in it, or sometimes there are just some atoms missing or misplaced or whatever. And there are all kinds of defects. And there are some properties that remain despite defects. So for example, superconductivity is one of them, or many other properties that I talked about, like strength and so on. They might remain despite defects, but others are completely ruined by even the tiniest of defects. And it's really hard for a computer to simulate what would happen in an imperfect material. Just that's the nature of imperfection. You don't know how it will be imperfect. And so this is another thing that's standing in the way of computational materials science solving all of the world's problems. So this is all I had, and I will take any questions from you now. Thank you.